Hi, everybody. Well, this has been really a great conference. Like everybody else here, I'm sure I've learned a lot too. And watching all these fantastic, really inspirational talks, I feel very privileged to even be here and for the opportunity to present alongside all this great work that's really pushing AI to really exciting places in image reconstruction. So my affiliation is my disclosure. Actually. I work for Siemens Medical Solutions, as you might have guessed by my first slide. I'm part of the PET Physics and Reconstruction group in Knoxville, Tennessee. And with this talk, I hope to provide some perspective from our industry point of view and also introduce you to some of the work that we're doing in AI and molecular imaging. I will start by showing this slide, this plot, which I'm sure lots of you have seen some sort of derivative of. And this represents the explosion in the interest of AI in the recent years. And this is a combination of several factors, but in particular, AI is producing state-of-the-art results across many tasks and many disciplines, and advances in hardware and software, they're making these tools more accessible. And you'd be hard-pressed to find even now a field which hasn't been affected and even transformed by AI. And as we know, medical imaging and image reconstruction is no exception. And so I'm very excited about this. I think we're sort of on the precipice of a revolution, and I think it's an exciting time, and I'm very optimistic about the prospects of AI. So Siemens is no stranger to AI. They've been in the game for a long time. They actually are one of the world leaders in healthcare-related AI patents. They have invested a tremendous number of resources into the AI space, and this has helped to procure an incredibly large repository of medical imaging data, and even a supercomputer named Sherlock, which has enough petaflops to make Skynet jealous. But we have 200 dedicated scientists across the world at multiple sites working very closely with clinical experts to try to identify the real medical problems and come up with creative and new ways to try to address these problems with AI. And the result of this effort has been a large assortment of AI-driven applications which are already available in the product. And these include things like automatic annotation, segmentation, lesion detection, identification, segmentation, and all of these are across multiple modalities. Within molecular imaging, we are also seeing some AI-related applications come to maturity. For example, we have something called flow motion AI, where we use an intelligent algorithm for organ segmentation, and this helps tailor continuous bed motion scans specifically to the patient and helps improve patient workflow. We have something called OncoFreeze AI, which was introduced to address respiratory motion within the PET reconstruction. And we use AI to identify the optimal space within the emission data to extract the respiratory waveform for use in the motion correction. Multi-parametric PET AI uses artificial intelligence to automatically segment regions in the arterial blood so we can automatically extract image-derived blood input functions for use in compartmental and fully quantitative parametric analysis. And we have also one more I wanted to mention. I won't mention all these, but auto ID is a smart algorithm for automatically identifying and segmenting areas of abnormal uptake in PET images, and at the same time differentiating them from normal physiological uptake. And so a lot of these, actually all of these are currently available on the system. And so I'm not going to spend too much time talking about these, but I chose in the later part of the talk to introduce you more of the current work that we're doing right now, stuff that isn't quite so mature as this, but stuff that I find just as interesting. So within our group in PET physics and reconstruction, we can pretty much classify our AI efforts into three general categories. And we classify these as system hardware and detector systems, those that are related to the reconstruction, and those that are related to post-reconstruction. Within the hardware bubble, the blue bubble in the middle, we're investigating ways we might use AI to improve the speed of QC and system calibration protocols, and also looking to see if we can use artificial intelligence for improving detector performance itself. For the reconstruction, this includes absolutely direct reconstruction. We're investigating this and and the robustness to noise. But also we're looking at AI for speeding up traditional iterative reconstruction. And so EM reconstruction could typically be regarded as a balance between convergence and noise. And we're wondering if we can use AI to produce good quality images from inputs that are noisier or non-converged. And within the reconstruction bubble there, we also include the corrections we have to do to the emission data, such as attenuation and motion. And in the third bubble, the last category here, the post-reconstruction, we include image processing like denoising and registration, but also some other tools for helping to facilitate the interpretation of the images in the clinical setting. And so I will go from there, but before I do this, I would like to present a very philosophical question. Why are we doing AI? We're not just doing it because it's cool and fancy. We do AI because it's a very complex network and it allows us to solve problems that we were unable to before. It's a very flexible framework, and if we present a very simplified supervised paradigm, we provide a start point and an end point, and we let some network connect the dots. It's able to map the pathway from the input to the output domains through complex levels of abstraction and pattern recognition. And because of this, we find that these AI algorithms have demonstrated impressive robustness to noise in our data. And this is a very important consideration for molecular imaging data. But also because of this, we need to evaluate these things very carefully. And this has been the recurring theme today we've seen in a couple talks, but we must evaluate these in ways which are consistent with the clinical needs. And this is a very important part of this, especially coming from the industry. And I'll give a couple examples before I move on, but in this first one on the left, I'm showing that we can generate an image using a direct deep learning reconstruction, as we've seen from some of the other presenters today. But why would we do this when we have an iterative algorithm which includes physics and analytical projectors? So we know exactly what we're doing. Can we expect better noise properties in the image? Probably, almost certainly. But we need to make sure that we preserve quantification across the entire field of view. Is this reconstruction going to be fast? Oh yeah, it's much faster than iterative reconstruction. But still, we need to ask ourselves the question, is speed really necessary if a nuclear medicine physician is going to read the image the next day or the day before? So some of these arguments really fall apart when we place this in a clinical context. So along these lines of thinking, we may assume that maybe we use deep learning for maybe very sparse count data, or maybe if we need to reconstruct a lot of frames of a dynamic protocol or multi-time point imaging protocol. But even then we need to check the quantification, because after all, we have a precision measurement device and we need to preserve that quantification. That's what we pride ourselves on in PET. Moving to the center, it's a similar thing with PET denoising. We know that we can suppress high frequency noise in the images with AI, and this has been demonstrated by almost everybody in the room. We know we can do this, but the question is, what are the clinical implications for this? Does this improve signal detectability, lesion SNR? In a lot of cases it does. But then you have to ask yourself, if a physician sees this image and they see the other image, does it actually change the interpretation of the image? In other words, would the physician be able to detect this lesion, overread through the noise? And perhaps it doesn't make any difference. So we really need to keep this in the back of our mind. And we also can't discount the possibility that we've seen in a couple times today that sometimes we can actually suppress lesion signals doing this. And we can hallucinate or boost up artificial structures, which really aren't there. And this in itself is dangerous, but now we may present a physician an AI enhanced or AI denoised image where the noise properties in the image don't reflect the quality of the data in the traditional sense. So this might actually inflate the confidence, give the reader a very high amount of confidence in an incorrect decision. And this is equally as dangerous. And so this is certainly something to consider. We can also synthesize synthetic CT or synthetic mu maps from the uncorrected emission data themselves. But can we expect that these emission data are going to provide complete information about the attenuation? Probably not. But can AI do a good enough job to get a good enough attenuation map for the corrections? It's possible that in most cases it can. But it's also possible that sometimes, at some point, it's going to fail. And we need to understand what are the limits of this. And moving forward, if we apply this model to a different tracer, perhaps a more specific tracer, we might expect that in parts of this synthetic data, it's poor quality. And so qualitatively, it would look terrible. But on the converse side, is it good enough for the corrections? Which it may be. And so we need to investigate these while keeping our eye on the goal. And so for the remainder of my time, I'm going to talk about some of the actual work that we're doing. But I first wanted to mention time of flight PET because this impacts everything we do. It's very important to what we do. By measuring the coincidence timing in our measurements, we improve signal SNR in our emission measurements. And this translates directly into the image by enhancing signals and suppressing noise. But it also has the benefit of improving some of the corrections we have to do, for instance, attenuation. But not even considering the corrections, we have customers asking us why in our new scanners our uncorrected images look so closely to our corrected images. And even if we remove the reconstruction altogether, we can use the timing information to directly deposit the annihilation events directly back into image space within some certainty related to the system timing performance. And in the current generation of the scanners, the timing performance is around 200 picoseconds. So this translates to about a few centimeters in image space. So you can think of these histo images as generally as blurred and slightly noisy versions of their fully reconstructed image correlates. Enter AI. And so this presents a great opportunity for a convolutional neural network because now you have a representation of your acquisition data directly in the same space as your target image. And this is relatively a straightforward problem for a convolutional neural network. So we're investigating this with our collaborators at the University of Pennsylvania. And this group did a lot of the early work on histo images and direct recon. And now we're looking at this in the context of, can we achieve accurate quantification? And can we perhaps use this for incorporating some sort of motion correction in the PET reconstruction? This is another thing that's related to, so the time of flight that I showed in the last slide, in the last couple slides, is dependent in part on the detectors we use in our systems, which is LSO. But the lutetium-176 in the LSO has another property which makes it attractive for another reason. It emits a tiny amount of background radiation in the form of a positron with cascadal gamma rays. And two of these gamma rays have energies at 200 and 300 keV. And if we open up our energy window on our system, we can use this to, in coincidence with both our 511 keVs, to identify which events came from the positron annihilation in the crystal, especially by using the time of flight information to find out where exactly it came from in the crystal. And so by reconstructing these data in a separate window, we get an idea of the attenuation of the subject. And we can compare this to a blank scan, and then we can use this as an attenuation map specifically for the corrections in the reconstruction. Now, as you see in the center, we can achieve this measurement, this transmission measurement, even with the tracer on board, even when the subject is hot, but the data are very noisy. But this serves as a good prior for an MLACF or an MLAA algorithm, and it sends kind of clean it up. But it's still not perfect. Since it's a multiplicative term, we still experience crosstalk effects in certain places of the images. So you can see in the bladder there, it's photopenic and it's not exactly accurate. But this is another avenue that we're investigating for artificial intelligence. And so this is some recent work that we've done with the University Hospital in Bern, and they've done this on the Quadra, which is the long axial field of view scanner they have there. And so the idea is that you obtain this transmission measurement, you reconstruct it, you use it as a prior for an MLACF algorithm, and you take that output, which is improved and less noisy but not perfect, and train this even in a supervised fashion against real CT or MUMAP data, and we can improve the quality of this. And we've shown, and this is a relatively also easy task for a convolutional neural network, and we found that, I didn't have much to do with this, but my colleagues found that this improves the quality of the MUMAPs and the reconstructed images and the quantitative PET values. Sorry, going the wrong way. So this is the last one I'm going to present, and I might actually be a little short so we can have some discussion about this. But we're also looking at improvements to the attenuation correction in different ways. Since the invention of PET-CT over 20 years ago, we're using a separate CT image, a separate CT X-ray transmission image for the emission corrections. And because these are taken at slightly different time points, we often see that these are misregistered with respect to each other, and this introduces quantitative artifacts in the reconstructed images. So this seems like a good application for something which, a synthesized CT directly from the emission data themselves, or even the transmission, which I covered in the last slide. But the point remains that the CT is acquired not just for PET attenuation correction, but it serves a diagnostic purpose as well. And since we already have it, we'd like to use it. So we're investigating deep learning for providing deformable intermodal registration. And so the idea behind this is that we have a couple different convolutional neural networks. The first one is meant to take either a CT image or a PET image, the same network, and basically extract from it a set of feature maps. And then we do this equivalently for the CT and the PET, and then you concatenate these together, and a downstream convolutional neural network is then able to regress the deformation or the motion between them. And we found that we can use this motion field to then resample the CT to match the PET distribution. And we've investigating this in the context generally of whole body imaging, for static whole body imaging, specifically for FDG, but some other tracers. And we found that this method, it's performing quite well, and we're getting some encouraging results for estimating respiratory motion, but also bulk movement of the head and the arms and the legs and feet and things like this. And so right now we're in the process of investigating other ways we might apply this technology. We're still investigating this and evaluating this and realizing various noise levels and seeing how it behaves in the presence of really noisy data. But we're wondering if we can extend this technology towards slightly different applications. So for instance, we could potentially take a single CT and apply it to every single phase of a respiratory gated series. And then we can improve the attenuation, essentially matching the attenuation for every. And you can imagine that something similar could be applied towards a parametric set of images, or even images which are acquired on different days. Say you have an immuno-PET patient and you want to scan him consecutively on different days. Can we use the same CT and just match it to the uncorrected PET distribution? And we're also investigating this in the context of intramodal registration, intramodal estimation of motion vectors for incorporating motion correction within the PET reconstruction themselves. And so in conclusion, we're currently focused on AI as a tool, but we're focused just as much on the evaluation, because we need to evaluate these things in a clinical context in ways that reflect actual needs in the medical setting. And for this, we're leaning on the experience of our clinical and our academic colleagues. And without these collaborations, our work would really be meaningless. And so with that, I'd like to acknowledge just a few of our collaborators, which have directly contributed to some of the material that I've presented here. And thank you very much that's all I have. Thank you very much for your attention. Appreciate it.
We have time for one question.
Thank you. For the LSO background, that project, the data you showed, the 5 minutes, is that 5 minutes from regular scanner or 5 minutes from total body PET?
This is from the total body PET.
Okay. So is the approach feasible for conventional scanners at the 26,
it was
26 centimeters?
It was first investigated on the vision scan, the standard field of view vision scanner.
Is the noise level sufficient for if we apply this on the
they were able to do it also. Yeah.
Okay. Thank you.
But you're right, with the enhanced sensitivity, we do get better statistics from these. Yeah.
Did you use both gamma spectrums? Mutation.
Well, we use these just to classify the coincident 511s, and then we can reconstruct those.
All right. Thank you, Joe.
Thanks, appreciate it.